Okay, welcome back. So I have a new puzzle called the Lich's Nemesis. Today will be a little bit different because I actually want to talk about some of the math behind this puzzle. The geometry I think is new. I don't think this has been explored by puzzles yet, or any other twisty puzzles. So it has 11 faces, top and bottom. It has three faces perpendicular to the top and bottom going around, and then it has these trapezoidal faces here. So the angles, let's talk about which faces can exchange pieces. So the dihedral angle, and we'll talk more about these angles. The dihedral angle from this face to this face is the same as the angle from this face to this face everywhere around the puzzle. This is a different angle, and that means that we can exchange pieces like so. This can move around. We'll have to do something like that if we want to keep mixing, and in this way you can quite easily mix up the entire puzzle. So I was really happy with the quality of this. Like, this turned out absolutely great, and it's not too many pieces either. So I was really happy with how it turned out, and the geometry is fairly interesting in its own right. So where would you get this shape from? In fact, this isn't the true shape that you should associate with the puzzle. The axis system, the way I think about it, is you want a solid. Now, this isn't necessary. You want a solid where when two faces are adjacent, they should have the same dihedral angle as every other adjacent faces. So let's actually jump into these questions with polyhedra. So I wanted to share some of the math that actually led me to this solid. And there's a really cool math question here. So polyhedra, what is that? Just jumping into 3D space, you throw down a few points and you can connect them up via straight lines. Maybe you have a pyramid, maybe you build your platonic solids, but you have flat faces, you have straight lines, and you have vertices. And for the most part, we only consider like convex polyhedra. So this means they're roughly rounded. So we could talk about polyhedra in 3D. Now for a twisty puzzle, we have an added question. Let's say we have our polyhedra right here. Let's do something perhaps a little bit unconventional. Okay, something a bit like a prism. You also need to consider, is there an origin? Maybe there's more than one origin to a puzzle. If you are interested in that, the mosaic cube is like the classic example of a multi-origin puzzle. But for us, let's think about a single origin. And from that origin, you will have a unique vector that is orthogonal to each face. So these would be like, if you have a polyhedra you want to build a puzzle out of, you pick an origin for it. There should be usually a natural origin to pick, and then there are axes. These will be the axes of rotation for that puzzle. And then the next thing you need to do is, for that axis of rotation, you need to pick a cut depth. There will be a depth at which you need to make a cut with some 2D sketch that will allow the puzzle to rotate, cutting through that plane. So there are several choices that go into this. The next question is, if I give you a polyhedra could be all sorts of not regular. There are no limits. It could be any sort of graph that fits on a sphere. The angles could be all different and all wonky. When can you take a polyhedra and turn it into a puzzle? And this question mainly has to do with the angles between axes, because it has to do with something called the dihedral angle. If I make a turn here, I want the axis for this face to rotate with it and line up perfectly with that axis. So if you draw a picture of it, we have one axis here that we're rotating about, and let's say there's another axis here and another axis there. We want this axis to rotate into the new axis. And this means when that happens, if we have the same cut depth everywhere, you can make a new turn. And at that point, you have something that should scramble. And my cat may choose to interrupt, but we'll try and do this in one take. So, let me tell you what a dihedral angle is. You could talk about an angle phi between the axes. Or equivalently, if I have two axes here, let's say these are my two axes, I will have a plane here, and this axis will determine another plane there. Well, this angle on the inside, that angle theta, is called the dihedral angle. And I have a question. There are a few questions we could ask. The first question is the following. The first question is, let's say I have a list of polyhedra. So I'll write maybe a triangle, and then I'll have, let's say, my best shot at a dodecahedron. Not going to be great. Okay. We'll have a list of polyhedra, the first polyhedra, the second polyhedra, third polyhedra, and so on. And I want the number of faces. So this has 4 faces, this will have 12, and then we'll have the number of faces as we go along. I want the following thing. The number of faces, this is the number of faces for the nth polyhedra. I want Fn to go to infinity as n goes to infinity. So I get more and more and more faces, and you think it becomes more like a ball, right? It's like a big soccer ball with many, many patches. And here's my question. It's not really my question. I found this online, but I thought it was a fascinating question, and it surprised me. Let's take, let's say polyhedra 1, polyhedra 2, polyhedra 3, so P1, P2, P3, and so on. Let's take the maximum dihedral angle. Of Pn, and let's call that theta n. What happens to the maximal dihedral angle? So you think as it gets bigger and bigger, let's say something like this has 24 faces. As that dihedral angle, or as the number of faces gets bigger, it should get more ball-like, and that dihedral angle should get bigger and bigger until it becomes almost flat. Does theta n have to go to 180 degrees? And what surprised me is this is false. This is not true. In 3D, polyhedra, as the number of sides grows, their dihedral angles could limit to something smaller than 180. Essentially, the angles between faces there's a certain sharpness, not exactly sharp, but there's a certain sharpness that you can keep no matter how many faces you add. if you pick the right kind of polyhedra, if you pick them very carefully. So why is this surprising? Let me go to 2D. Let's take this question and go to 2D. If you write down a polygon, doesn't matter what the polygon looks like, this would be the maximum dihedral angle inside the polygon. As the number of faces of the polygon goes to infinity, that dihedral angle definitely goes to 180 degrees. In 2D, this is true. Theta n does go to 180. What happens in 3D? What goes wrong? Let's talk about the example, and that's actually where this gets its geometry from. So what is the 3D example that we get? The example in 3D. So I can't claim to be the person who solved this. This was an exercise on a book on polyhedra. I forget the author. I think it's Pack. Actually, I can look it up. But the example here comes from rectified prisms. If I can spell rectified prisms. So if we take a prism, what does rectifying a prism mean? Let me draw a prism here to the best of my ability. Rectifying a prism, you do the following thing. You take the midpoint of every edge, and for every corner, you just chop it off at those 3 points. You cut off that corner. And the process of rectification here will leave you with, you'll still get a pentagon in the middle after you've cut off all of the corners in that way. So we'll still have a pentagon in this example. But now we'll have the following shape instead. We'll have a new point there, sort of like an accordion. Kind of like an accordion, kind of like a drum sort of look. We'll have a new polyhedra that looks like this. It'll have, if we have an n-sided and n-gon, how many sides will this have? We will have 3 times n going around the sides, because we have this side, that side, and those, and just copy n of those going around, plus the top and the bottom. So this is actually kind of cool already. 3 times n, if we have n equals 3, we have 9 plus 2, so 11. N equals 4, what do we have? 12, 14. Yeah. 12. Okay, n equals 5, we would have 17 sides. 11, 14, 17. As far as shapes go, this is kind of a strange number. Like platonic solids, they don't have numbers like this. I mean, a couple prime numbers showing up. It's kind of odd. But the cool thing is if we stretch, vertically in the appropriate manner, if we stretch vertically, then how many edges are we dealing with? We're only dealing with like this edge, an angle there, and we're dealing with an angle here. And then everything else is symmetric to those. Every other edge is symmetric to one of those two. So as you squish it, you flatten out that angle and you make this angle sharper. And so there's going to be a balance somewhere in the middle where the dihedral angles for these two different types of edges for the rectified prisms match. We can make all dihedrals match. And this occurs at the following dihedral angle. So you can sit down and calculate this, and it ends up being inverse cotangent of negative cosine of pi over n, where n was the original n that you picked for the n-gon. So if you look at this number, think about, well, what does this number do? As n goes to infinity, what happens here? Cosine goes to, well, cosine of 0, so negative 1. And then we have inverse cotangent. Well, this inverse cotangent, in case hopefully I didn't make a mistake, this actually limits to 135 degrees. That's well shy of 180. This family of examples, these are solids that have an extra property. Every pair of faces that are next to each other have the same dihedral angle across the entire solid. And in this sequence, you get infinitely many faces in the limit with a bounded dihedral angle well below 180 degrees. So this serves as a counterexample to that question earlier. It also gives us a nice family of solids to turn into puzzles. Every single one of these, in principle, could be turned into a puzzle. And this is the first one. This is number 3. It has 11 faces, top and the bottom, 3 going around here, and then 3 for this trapezoid and 3 for this trapezoid. 3 times n plus 2. Okay, so that's pretty cool. That's to me, that was very surprising. You can ask why does this change from 2D to 3D? And part of it has to do with, in 2D, if you have a polygon in 2D, then there's a relationship with the number of sides and the sum of each of these dihedral angles. In 3D, the situation is far more complicated. In fact, there is no equation relating the solid angle equivalents for the vertices to the number of sides of a polyhedra. It's just not a thing that happens anymore. So you can go through different routes with the Gauss-Bonnet theorem for polyhedra, but I'm not going to get into that for sake of time. What I will say, I want to say one more thing, just kind of map out an interesting thing, and that is polyhedra with one dihedral angle. What is here? And in fact, you may think, okay, nice polyhedra that are symmetric. What is this like? Okay, you got the platonic solids and you have some extra stuff. There's a classification somewhere, right? To my knowledge, no. I have not found, I'm a mathematician. I have not found a classification of these. I've searched a fair bit, flipping through some PDFs on research on polyhedra. I'm not aware of any sort of classification. In fact, you can ask a harder question. Is such a classification possible? It's one thing to say, like, okay, we have polyhedra with one dihedral angle. To classify something, you pretty much have to be able to count it. And we've already seen here, well, this is one collection of examples, an infinite family of examples. Let's talk about other infinite families. What is here, first of all? Platonic solids are here. The Catalan solids are here. There are actually two Archimedean solids that have this property. There are some infinite families. We have bipyramids. We have the trapezohedron. It should be, it's trapezohedron, the various different trapezohedron. I'll sketch one of them. And we have the rectified prisms. And we'll sketch these out. Okay, bipyramids are really simple. Take a regular n-gon and make a pyramid out of it, and then make a reflected copy. The trapezohedron is very similar to this. You essentially have what looks like a pyramid, but you have a zigzag matching them up. So one pyramid is like offset by half from the other one. So you have the trapezohedron, and these both have the same property that you only have so many edges. You only have two. This dihedral, that dihedral. This dihedral, that dihedral. And you squash it until they match. The same thing that happens with these rectified prisms. So I'll sketch this one again to the best of my ability. Okay, not a perfect sketch. In fact, that edge shouldn't be there. But both of these have this very like flat, there's a bilateral symmetry to them that make these infinite families possible. Let's sketch out the dihedral angles that show up. So if I sketch out what dihedral angles show up, this will be theta. The single dihedral angle that shows up for these solids. If we go to, where are the platonic solids? Tetrahedron, starting off around 70.53. This is your tetrahedron. Your cube, of course, at 90 degrees. And then we have the dodecahedron, 116. Let's put 135 here, and let's put 180 there. 135, so 116, I don't know. I'm just going to throw it down. We have the dodecahedron. We have the dodecahedron. But we also have the Lich's Nemesis. That actually belongs here as well. This is the 3 rectified prism from this family. And then if you look at the rectified prisms, let's actually plot a few more. I skipped the octahedron. Octahedron lands here in the middle. We have our octahedron. It is one of our bipyramids, for one. Dodecahedron, and then icosahedron shoots past our limit of 135 with 138. So these are platonic solids. And the rectified prism, the first one, actually lands in the same place as the dodecahedron. Think about that for a moment. One has 11 faces, the other one has 12. Like already you can see the relationship between dihedral angles face count, edge count. These things are just not simple in 3D geometry. And let's think about the infinite families. Well, the rectified prisms, you're going to have an infinite family that limits to 135. Bipyramids, well, our octahedron was one of them. There's another bipyramid further down the line, further over here, the triangular bipyramid. I didn't look up the exact number, but these will continue to limit, and they'll limit to 180. And the same with the trapezohedron. We'll have another infinite family that limits to 180. And then you can start stumbling through the Catalan solids. If you go through the Catalan solids, the rhombic dodecahedron starts at 120. So we have 120 here with the rhombic dodecahedron. The triachus tetrahedron is 129 point something. The pentagonal icosahedron, already we've blown past 135 with 136.3. But our Catalan solids are scattered through here, and we'll have other solids as well, like the two Archimedean solids, they're here as well. What is going on here? We have two limit points, 135 and 180, and a lot of stuff scattered in the middle. Our infinite families come in these three classes. I'm not aware of another infinite family. It would be fascinating to see if there were some more complicated non-bilateral infinite families. I kind of think that would be tricky. Can you perturb a solid? Let's say, is this actually classifiable? Here we just have a bunch of things that we've thrown down. Here's question 2. This one has been answered, but it's been answered as a research problem as of last year. Question 2 is, can a polyhedra and let me clarify this. There's a lot of data for a polyhedra. One of them is just combinatorial data. You have the graph and maybe a rough idea of how to sketch the graph. Of course, everything decides to make noise right now, but let's carry on. You have like just the graph of the polyhedra on the sphere. Well, then you have the geometry. What are the exact angles? Can a polyhedra graph, just the graph of the polyhedra, be realized as a single dihedral solid with a continuous family of different dihedral angles, with theta varying continuously? So this is a kind of rigidity. Do polyhedra have rigidity with respect to dihedral angles? And this is a really tricky problem. There are various classical theorems by Euler and others about different types of rigidity that polyhedra have. In fact, I think the Euler one is if each face is like a plate, a rigid plate, and they are connected by hinges. Can a convex polyhedra vary continuously? And in fact, he proved that no, they can't. This is a lot harder. The exact geometry of the faces can change. Those could be stretched. The only thing we're asking is that the dihedral angles all match each other. And this is actually characterized by a conjecture known as Gromov's dihedral extremality conjecture. For convex polyhedra. So this was actually resolved last year by some researchers at Harvard. So this was actually answered. I won't state the full thing because I would need to talk about Riemannian metrics, but and different kinds of curvature. But this was actually answered in the affirmative. Last year. I should state who answered it. It was Jinmin Wong, and I will probably butcher names, so I'm not even going to try. And then these three mathematicians actually answered this question. They are rigid, which means something very fascinating. This set of polyhedra is actually countable. You can't have any sort of continuous family. In fact, the graph of the polyhedra tells you it has only at most one, most likely no realization with a single dihedral angle. And since finite graphs are countable, this set is countable. But it's clearly quite complicated. It has this extra limit point at 135. Are there other limit points? There are a lot of really cool questions we could ask here. Are there other limit points between 135 and 180? Can these solids be classified? Just the fact that answering whether it is possible to classify them, maybe there's a continuous family, only happened last year, and they used methods from the Dirac operator and spin structure from like quantum mechanics to solve this problem. The fact that that's what it took to answer whether it's possible to classify them means that this is a tricky problem. And in principle, one of the fun side effects of this is every single one of these could in principle be a puzzle. And most likely every single one of these would scramble, at least at a basic level. What are these solids? I'll just leave it with that question and this fun puzzle. I might make another video just dedicated to showing this puzzle. But yeah, I'll leave it there. Hope you enjoyed.